Number 8 from Chapter 5 of Knight's college physics book. They give us an acceleration versus time graph. They tell us the mass of the object is 500 grams. We need to convert that to kilograms. They ask us to draw the force, the x component of the force versus time graph. They're telling us that this is an x component of acceleration versus time graph. One thing that I'm putting down for the assumptions for this one, when the question asks us to plot this, they tell us this is the acceleration graph. They ask us to draw the x component of the force versus time graph. The one assumption I'm including here is that when they say the x component of force, that they must mean the x component of the total force, because that's the only way it would equal m times a. So that's the one assumption I'm putting in here. Then there are 4 sections to this graph: section 1, section 2, section 3, section 4. So there are 4 sections for this acceleration versus time graph. There will end up being 4 sections for the force versus time graph. I'm going to end up using this application of Newton's second law. We can use that to find the force for section, or the total force for section 1 and section 3, spots for which the acceleration is constant. And then parts 2 and 4, those, as in all cases, the total force should be proportional to the acceleration in that same direction. And since this is linear for section 2, the force versus time graph should also be linear for section 2. The same goes for section 4. Since this is linear, this 4th chunk of the graph is linear in the acceleration versus time graph. That 4th chunk should also be linear for the force versus time graph, total force versus time graph. So if I find this first chunk and this second chunk, then I can just linearly connect this point to this point. And then likewise for chunk 4, I can linearly connect this data point, or equivalent for the force graph, to a 0 spot. Chunk 1, this chunk. I'm just saying total force is m times a. They told us the mass is 500 grams. We have to convert that to kilograms to get newtons. So 0.5 kilograms. And then that acceleration is 1. So that gives us a total force in the x direction for that first chunk of 0.5 newtons. Going on to chunk 3, total force is m times a. I get 0.5 kilograms times a negative 0.5 meters per second squared, gives us total force for chunk 3 of negative 0.25. Then I drew out this rough graph, and as I go through to plot these lines, I guess I should probably put the time on here as well, right? There's 1 second, 2, 3, 4. And the total chunk for the total force for the first chunk should be 0.5 newtons. So that's down here. And for that first chunk, it's for 1 full second. I'm looking up at this graph. It's 1 full second for that first chunk. So this will be 1 full second for that first chunk. Now, truth be told, my graph, this value should probably be up higher, right? I have my graph not taking up as much of the plot that I'm making on my graph is not taking up a huge chunk of my graph, but for right now, we'll continue on with it. Then chunk 3, I know my total force is 0.25 newtons, and chunk 3 goes from 2 seconds to 3 seconds. So from 2 seconds to 3 seconds, my total force should be negative 0.25. So I'm going to draw that section there. And then we already discussed how if this is linear here, this should be linear here. I don't have a ruler with me. I'm just going to use this other pen as a straight edge. There we go. Then we end with an acceleration of 0. And as we've said, I'll write this down just to make sure we can see it this way. Newton's second law, total force is mass times acceleration. If it's total force in the x direction, it's acceleration in the x direction. And the reminder then that these are proportional. So whatever happens to this, if this doubles, this doubles, if this halves, this halves, if the acceleration is 0, the total force is 0. So since up here we end with an acceleration of 0, that means that here we should end with a total force of 0. There you go.